Hi everybody, welcome to the last section that we cover in linear algebra, section 7.2, quadratic forms. Quadratic forms on Rn is a function q defined on Rn whose values at a vector x in Rn can be computed at x transpose Ax, where A is n by n and a symmetric matrix. A is a symmetric matrix. In that case, A is called the matrix of quadratic form, and this is called the quadratic form. So we have x transpose Ax. So x is vector in Rn, so it is a column n by 1. A is an n by n matrix, and x n by 1 but transpose, so that becomes 1 by n. So when we multiply all of this together, this is just going to be a number 1 by 1, so it's just a number. Right. Let's see, compute the quadratic form for the matrix and just the generic vector x. So we're going to have x transpose Ax, x transpose x1, x2, a 3, -2, -2 and 5, x1, x2. Right. Simple enough, it's just matrix multiplication. So let's multiply this. It doesn't matter because matrix multiplication is associative, so we can just take any two. Let's just do this one first. So I have x1, x2. Right, multiply these two together. 2 by 2, 2 by 1, so we're going to have a 2 by 1. So 3x1 minus 2x2 minus 2x1 plus 5x2. And multiply that out. We're going to have x1 times 3x1 minus 2x2 plus x2 minus 2x1 plus 5x2. So multiply out 3x1 squared minus 2x1 x2 minus 2x1 x2 plus 5x2 squared. Before we combine like terms, notice the coefficient 3, -2, -2, and 5. Right, now we just combine the like terms. Right, so notice that when we have the square, we're going to just have those numbers on the diagonal. That should be easy. And then it is symmetric, so those coefficients will combine together, give us this coefficient. So it is symmetric, so we split that in half and put that across the diagonal. Right, so that's how we do. Now we turn this back into the quadratic form if we have in that form. So once again, this should be a matrix. It should be a vector. Right. So let's just write this out. We have a square 1, 5, 3, and 2. So we know for sure those will be an element in the diagonal. Only that we can put x1, x2, x3, x1, x2, and x3. You see 5x1 times x1, 3x2 times x2, and 2x3 times x3. Right. Now for the mix, 1 and 2. So 1 and 2 is going to be here and here. So we look at this as -1. Coefficient of x1 and x2. So we're going to split that in half. And then here we have 8 is 2 and 3, so 2 and 3 is going to be here and here. We'll split that in half. And then 1 and 3, we do not have anything, so just going to put 0. Right. So that's how we construct a matrix, a symmetric matrix for quadratic form. Right. All the square will be on the diagonal, and then all the mixed term we just split in half and put that across the diagonal. Right. Now let's do that, but we compute for the values of keep doing that. Keep x for x equal to the vector of -3 and 1. So we're just going to put -3 and 1 in here, pretty much, right? Right, so x1 is -3, x1, x2, x2 square. That would be 9. 24 minus 5, 28. Right. So that is one way to do that. Another way to do that is rewrite this as a matrix, as x transpose AX. The matrix would be transpose. We have 1 and -5 on the diagonal, and the other is -8, split in half. So that is the quadratic form in the vector form, and now we're just going to put -3 and 1 in it. So Q right. Let's multiply this first. -3, -4, 12. So mean 12 minus 5. So that gives us -3 times -7, that's 21, plus 7, so that's 28. Of course, they should be the same. Right. So we see that a quadratic form can be written as a symmetric matrix. So why do we write that as a symmetric matrix? Well, from the previous section, we know that if it is a symmetric matrix, we can orthogonally diagonalize it. So we can diagonalize it and turn to something nice. Now, this is the purpose of one of the purpose of rewriting the quadratic form. Now, if x represents a variable in Rn, then the change of variable is an equation of the form x equal py and y equal to p inverse y, where p is invertible matrix and y is new variable in Rn. Here y is in the coordinate of x, relative to the basis of Rn determined by the constant P. Not only that, in this case we have A is a symmetric matrix, so this should be Q transpose Q, and then we just want to rewrite everything and turn into X equal to, let me write this out, it will be easier to see. X transpose A X. Now A is symmetric, which means it can be orthogonally diagonalized. Q D Q transpose X. In this case we can have X transpose Q, and then D, and then Q transpose X. A transpose of a product is the product of a transpose, so we can rewrite this as Q X transpose. Transpose of a product is the product of transpose in reverse order. So I can rewrite like that. D and then Q transpose X. Notice that here we have Q transpose X and Q transpose X. That would be Y transpose D. Y transpose D. Y transpose. Y. So this case Y is that. So this is Y transpose. So we turn a quadratic form into another quadratic form. However, this is a symmetric matrix A, but this is just the diagonal matrix D. So what is the advantage of doing that? Let's see in the next example. Make a chain of variable to transform this quadratic form into another quadratic form that does not have the cross product term, meaning that will not have the negative 8 here. Right. So first of all, of course, we rewrite this into a quadratic form in the vector form. So we have Qx equivalently equal to X transpose Ax. Just going to leave X and the matrix A transpose. The matrix A, we have 1 and negative 5 on the diagonal, and then the negative 8 have to split in half for x1, x2, and x2, x1, and then x. So A, in this case, the symmetric matrix corresponding to the quadratic form is 1, negative 4, negative 4, and negative 5. Right. Now we will orthogonally diagonalize A, and then we go from there. Of course, first we find Eigen Values. Which is solving the characteristic equation. Right, determinant be 1 minus lambda minus 16 equal to 0. Multiply it out. Negative 5, negative lambda plus 5 lambda, so that negative 1 lambda plus 5 lambda, so plus 4 lambda plus lambda square minus 16 equal to 0. That gives us lambda square plus 4 lambda minus 21 equal to 0. So that gives us lambda plus 7, lambda minus 3 equal to 0. So lambda equal to negative 7, lambda equal to 3. Just put the corresponding index. Right, so we have two eigenvalues, that to be expected. Now for eigenvectors. Which we solve this equation. Right, first for the eigenvalues of negative 7. Minus negative 7 is plus 7. So 8, negative 4, negative 4, and 2. Of course, if it's 2 by 2, we really don't need to do reduced row echelon form, because those two should be multiple of each other. So we just keep one row, that will be it. But I'm just going to use reduced row echelon form here. So x1 minus 0.5 x2 equal to 0. x2 is 3. So x equal to x1, x2. x1 will be 0.5 x2. x2 is 3. Factor out x2. Right, here we just choose x2 to be 2, so we don't have to deal with fraction. So we have x one, the eigenvalues is going to be 2 times 0.5 is 1, 2 times 1 is 2, so 1 and 2. And for the eigenvalues of 3, minus 3, negative 2, negative 4, negative 4, negative 8. Once again, they should be multiple of each other. The nice thing about this is, I need to do is change the diagonal to negative 8. Negative 2 to just 1, 2. Yeah. So x1 plus 2x2 equal to 0, and x2 is 3. So we have x equal to x1, x2. X1 is negative 2, x2, and x2 is 3. So factor out x2, and that's what we have. Right, and now we choose x2 to be just 1. So we have the eigenvalues of -2 and 1. Next, we just normalize the vector. Right, so u1 is x1 over the norm of x1 1 2 1 square plus 2 square. That gives us 1 over square root of 5 and 2 over square root of 5. So that is u1. u2 we do the same way. x2 over the norm of x2 square root of -2 square plus 1 square. So -2 over square root of 5 and 1 over square root of 5. Right. Of course, we don't have to show they are from different eigenspace for symmetric matrix, so they are guaranteed to be orthogonal to each other. Of course, we can verify the dot product is equal to 0. That's obvious. Right. And then finally, we can orthogonally diagonalize it. So we have now it is just simple. We're just going to say it, A is equal to Q dQ transpose. Right. So now we're going to write. Now we see why in this quadratic form they don't want to use the Q. Oh, that's fine. Yeah. It is that the script Q doesn't matter. Right, so we have X transpose AX. Now the organization, instead of A, we will have Q D Q transpose X. And now we're just going to say X. It's just going to be X if we just transpose Q. The matrix Q will be U1 and U2. So I'm just going to put them better in column here. So that's U1 and then U2. And the matrix D will be a matrix of eigenvalues of -7 and 3 on the diagonal. And then I just transpose this to row become column. Then column becomes row. And then X. Yeah, we don't need the page number here. Right. And after that we're going to say just this here is going to be Y transpose, and this here is going to be Y. So after all of that, we will turn the quadratic form here, like let's use the Q, the script Q X equal to YT7, -7 and 3. So we just say it's going to be -7 Y1 square plus 3y2 square. Right. So I'm just going to write the quadratic form corresponding to that. Of course, when the process of doing that, we reduce the cross product term of x1, x2. Now we just have the squares here. Right. I will try another example. Let A be, but before that, let A be n by n symmetric matrix. Then there is an orthogonal chain of variable x to py that transform the quadratic form x transpose ax into y transpose dy. So when with the process of doing that, we have no more cross product term like x1 x times x2, x1 times x3, x2 x3, so on. The columns of p are called the principal axis quadratic form x transpose ax. The vector y is the coordinate vector of x relative to orthonormal basis of Rn given by. Of course, all that it doesn't matter as long as you know how to change this into change this quadratic form into the one without the cross product term. Right. So we're going to do the same thing here. Let the left hand side let's say swift x. Right. Be x transpose a x. The matrix corresponding to that, we have 5 and 8. The square term will be on the diagonal, and the negative 4 here will be split into the other two across the diagonal, and then we have x. So now we're going to orthogonally diagonalize a, and we turn in that process we eliminate the x1 x2 term. Right. So same thing we did before. Eigenvalues, eigenvectors, normalize the vectors, and then we can orthogonally diagonalize it. Right. So eigenvalues. Right. So determinant, this is 8. So that gives us 5 minus lambda, a minus lambda minus 4 equal to 0. Right. So we have 40 minus 5 lambda minus 8 minus 13 lambda minus plus lambda square minus 4 equal to 0. So lambda square minus 13 lambda plus 36 equal to 0. So that is minus 4 and minus 9. So lambda 1 equal to 4 and lambda 2 equal to 9. Usually when we do this, we can check with the eigenvalues and eigenvector to work out nicely. Now find the eigenvectors. By solving this equation for non-trivial solution. Right, we have eigenvalues. The first one is 4. minus 4 x equal to 0 vector, which is 1, negative 2, negative 2, and 4. Right. Don't need calculator for this. Reduce to echelon form will be just 1, negative 2, 0, 0, 0, 0. So x1 minus 2, x2 equal to 0, and x2 is 3. Right? So in this case, x equal to x1, x2, x1 is 2x2, so x2 equal to 2 and 1. So I'm going to choose x2 equal to 1. That will be easy. So we have the first eigenvector corresponding to eigenvalues of 4. It's going to be 2 and 1. Now let's just normalize it because we may not have enough space later. So just normalize that. The magnitude or the norm is going to be square root of 2 square plus 1 square, so that's square root of 5. So it's going to be 2 over square root of 5. This is similar to the last problem. Right. So this is the unit vector in direction of x. Right. Now for the second eigenvalues, 5, negative 2, negative 2, and 8. Right. Going to be negative 4 and negative 2. Of course, always one of them is multiple of the other when we only have 2 vector. I mean, when we only have 2 rows. This will be 1 and 1/2. So we have x1 plus 0.5, x2 equal to 0, and x2 is 3. So x equal to x1, x2. x1 is negative 0.5, x2. Factor out x2. Then we can choose x2 to be 2. So we don't have to deal with fraction. So the second eigenvector is corresponding to the eigenvalues of 9. It's going to be negative 1 and 2. And here I will normalize this as well. So negative 1 and that magnitude also square root of 5. Right, and then with that, when we have orthonormal vectors for Q, we can diagonalize it. So A will be written as Q D Q transpose. Right. So in this case, A will be equal to Q, will be those two vectors stacked in column. And then D will be the matrix of the eigenvalues, the first one and second. So that's why I just put all the 1 and 2 so we know which one we put first. So that's 4 and 9. And then Q transpose, we're just going to transpose this. Right, and then finally for the quadratic form of X transpose AX, we can write like this. Which we just copy and paste. Right. And then we can let this be Y transpose, and this be Y. So this quadratic form in terms of X can be written as, for this matrix, 4y1 square plus 9 y2 square. Of course, in that process, we eliminate the x1, x2, and of course now we have the equation is 4y1 square 9 y2 square equal to 48. Right, so we have the equation. Right. Next, the last thing we want to cover is classify quadratic forms. So quadratic form will be positive for all x not equal to 0 and negative definite if less than 0. Less than 0 for all x not equal to 0 and indefinite if some of them positive, some of them negative. Once again, the quadratic form is X transpose AX. So if that is greater than 0 for every x not equal to 0 vector, then it is positive definite and negative definite if all that always negative. Right. There will be a lot of different ways to determine if a matrix is positive definite or negative definite. Since we have eigenvalues, then we just say positive definite if eigenvalues are all positive, negative definite if all eigenvalues are all negative, and indefinite if we have some positive and some negative. Right. Of course, so that is easy. However, what is the concept of positive and definite, positive and negative definite? Actually, we covered that in count 1, count 2, and count 3. I mean, some idea of that. So I wrote this for count 1. This is called the second derivative test. First, we always have to start with always have to start with the first derivative equal to 0. That gives us the critical point. And then the second derivative is greater than 0. That is positive definite, equivalent to positive definite, like it's concave up. So that is the local minimum. Second derivative is negative, concave down. That equivalent to negative definite, and that's the local maximum. And because if it is equal to 0, that's inconclusive. Okay. Now we go to count 2. Count 2, we don't have actually the positive and negative definite, but what we have is a Taylor series. A Taylor series like this, I only write up to the second derivative. Once again, the concept is the same as we have before. We want the derivative, first derivative equal to 0. So when we let the derivative equal to 0, that term equal to 0. So we just have that and the second derivative. Now, if the second derivative is positive, the square here is always positive, right? So the idea here is the square is always greater than or equal to 0. And we have derivative is greater than 0. So this term is positive if the second derivative is positive. So positive here, the whole thing is positive. So if we have f of x equal to f of c plus a positive number, that means f of x is always greater than f of c, right? Because f of c have to add something positive to equal to f of x. So in that case, f of c is less than or equal to f of x, so f of c is the local minimum. When this is negative, when the second derivative negative, the whole thing is negative. In this case, f of c is going to be bigger than f of x, because f of c bigger than f of x because we have a number have to subtract something to be equal to f of x. So f of c is bigger, so that is the local max. So the idea here, of course, the second derivative is kind of like represent the positive or negative definiteness. And then we go to count 3. Count 3, get back to the second derivative test. We actually have a symmetric matrix here for the second derivative of mixed partial derivative and everything. That's what we have. And same thing, positive definite, local mean, negative definite, local max. And in calculus 3, there's another way to determine if the matrix is positive or negative definite. But in here, in this class, we can use the Eigen Values to determine if the matrix is positive or negative definite. And that's all I want to cover for linear algebra. Thank you for watching.